All right, so let's begin. We are very so we are glad to have with us today again, and he will give the second lecture of his mini course on calculation of level sets of the Gaussian free field. Over to Subhajit.
Thank you, and thanks everybody who came for the second of this mini course. So let us start with a brief recall of what we did last time. We had a quick recap of the classical facts from Bernoulli percolation, and then we ended up asking the same question for a dependent, strongly so in a certain sense, percolation model on ZD. And the questions that we posed for this model were the following: that whether the strongly non-percolative regime and the strongly percolative regime, they extend all the way up to the critical point itself. Okay, so if you don't remember, so this is the definition for the threshold demarcating the strongly non-percolative regime, and beyond which, so when H is above A star star, okay, and again I would like you to recall that the convention, the direction of monotonicity is opposite to that of Bernoulli percolation for a model. So as the parameter value H increases, the model becomes thinner and thinner. Okay, so you will have fewer, less probabilities of this increasing events as H becomes higher. Okay, so this is the critical threshold above which you have above which the analyte crossing probabilities decay to 0 along a certain subsequence, and this is definitely above the critical point, because above the critical point it's definitely true. And the reason why we call it strongly non-percolative is this result by Rodriguez and Snitman 2012, where they proved that you have kind of similar properties that you expect from the strongly non-percolative regime in the Bernoulli percolation from this model as well. For example, the 2-point functions or the connectivity probabilities take stretch exponential in distance. Okay, so instead of like logarithmically big clusters, you will have polylogarithmic clusters. Okay, and before the result I'm going to present to you, the best that was known with regard to the relationship between A star and A star star was that they're both asymptotic with the same number as dimension becomes large. Okay, and then we talked about the strongly percolative regime, and we talked about why this event, as described here, is the correct event to look at instead of the slab percolation that we saw for Bernoulli percolation. Okay, and this also defines a threshold, which is H bar. And again, remember, keep in mind the reverse direction of monotonicity. So when H is less than H bar, you'll have the probabilities of this event decaying stretch exponentially. And I also showed to you, I think here, I outlined this argument. I think, yeah, it's basically this one, if you remember, where I showed that why this kind of events are the correct type of events that allow you to glue, this kind of the glue clusters in adjacent boxes to build bigger and bigger clusters. In particular, this gives you that below H bar, you actually have an infinite cluster with positive probabilities. In particular, in particular, H bar is less than or equal to H star. Okay, if you're below H bar, then you percolate. So you're definitely below H star. And this is kind of an exercise just to check, and still there, that this actually also gives you that, below H bar, you not only have an infinite cluster, but also you have a unique infinite cluster. Okay, so, if you're able to resolve this inequality, if you want to say that this one is basically equality, then actually you'll prove uniqueness as well for all of critical values. Okay. Now, so what is known again about the H bar and H star, except the obvious one that I just told you. One interesting thing that came out in this very interesting work by Druids, Prevost, and Rodriguez in 2018, where they proved that H bar is strictly bigger than 0. Okay. Now, what is the significance of that? Okay. So I think at the end of today's lecture, hopefully, you'll know that, and given that what I told you last time I showed to you this argument, if those of you who were there, that H star is non-negative, okay? And so, and at the end of today's talk, I'll probably be able to convince you that H bar equals H star. So you'll automatically know that H bar is bigger than or equal to 0. But this is something much stronger. It says it's strictly bigger than 0. So, in conjunction with the result that I'm going to present to you, it would say that the critical value is also strictly bigger than 0. But forgetting that, this is completely standalone, like it's independent of the thing that I'm going to talk about today. Now, why it is important? What it does tell you is that if you look at the, Gaussian free field, and if you look at these two sets, so phi bigger than or equal to 0, and phi less than or equal to 0, you can actually, because we are in a discrete set, we can forget equality sign. It's basically bigger than 0, less than or equal to 0, something like that. So these two sets are, they're both distributed, they're equally distributed, right? Equidistributed. Why? Because you have a symmetric field. So what does this tell you is that, you have an infinite cluster for this one, and so do you have an infinite cluster for this one. So they're concurrent, okay? And their interfaces, so that kind of, if you're in a continuum, it would somehow describe an infinite connected zero set of the Gaussian free field. And this kind of problem is very interesting in random real algebraic geometry, where you study different Gaussian, the zero sets of Gaussian ensembles of families of function. Sometimes, sometimes the eigenfunctions of Laplacians, and an alternative description, an alternative way to describe Gaussian free field and ZD is indeed to see it as a Gaussian linear combination of the eigenfunctions of the discrete Laplacian and ZD. Okay, so that's what I wanted to say, and that's why so this kind of results, this kind of techniques have potential applications to other areas of interest as well. And then actually you'll have this kind of things, usual suspect, but which are very interesting results, which says that assuming that you're below H bar, your Percolation clusters, the infinite clusters are kind of well behaved. So as I already, this is actually again, you can check it very easily, that the truncated correlation two-point function, which I described to you last time, if you remember, is basically, the 2 points are connected through a finite cluster. You can actually immediately deduce the stage exponential decay of that. You can compare the chemical distance of the infinite cluster, with the Euclidean distance. You can define a coincident variance, prove the coincident variance principle on the infinite cluster as well, which basically means that if you take a random walk on the infinite cluster, take the scaling limit, it converges to a bounded motion. All these kinds of properties actually you can derive, assuming you are in the strongly percolative regime. And recently there have been works for the last division bounds for disconnection estimates below H bar, assuming this thing with a series of beautiful works. Okay. Now, let me spend a bit of time in philosophical rambling, but that's important because, most of you basically will forget everything, and that's okay, because within 5 minutes after taking off from this talk, but something that I would like to take home from this one, and especially because now Tom has also given his lecture, is the following. And you have also seen from Tom's talk that one of the ardent percolation theory is to obtain context-specific characterizations of the critical value. Okay, when you would like to prove that, well, you have a very natural description of the critical parameter like PU or PC, but that immediately doesn't always seem to be good enough, right, to be able to say some interesting things for you. So, for example, then Tom had to define this, this limit for using the operator norm of the connectivity probabilities. And I think he also showed you, I think, the proof of 5PS argument by Hugo and Consol, where actually you have a different characterization, and then later you show that either this is equal to your all known critical parameters, or they had in certain type of relation. They're actually in certain type of relations with respect to your well-known critical parameters. And the characterization and the features of this new critical parameters are that they enable you to say something more specific. But then the challenge is that, of course, to prove that they hold their, they're equal to some or their critical parameters that you defined, or they're in a certain type of relationship with them. Here is the same thing. So let me just already give you an example. So if you have noticed that when I define A star star D, well, one could have equivalently define, I could just directly define A star star D as something above which you'll have a strict exponential decay. Okay, and then this problem will be boom. I mean, it's just immediately resolved. Well, of course, you can define whatever you want, but is that very helpful? I mean, what guarantees that the parameter that you define is even finite, right? But that was the reason you designed it in the first place. So that's why you'll start with a bit of weaker definition, which is you can assume that you can probably prove it using some other means. It's easier to prove that they're finite, and then use some other argument to prove. Use this property, which is definitely more than just saying that you don't have any finite cluster. You have actually some finite size criterions, which are very useful to trigger renormalization argument. I'll actually give you this proof actually because it's important to know in the next lecture. And then actually you can obtain this one as a consequence. Okay, but we did something opposite here. Here actually exactly what we did is that we came up with a condition basically that has been designed to give you this uniqueness, or this kind of large connection probabilities for free, essentially. Okay, it has been designed that way. Well, again, you can define that, and that helps you a lot. Although that helps you a lot to study the properties of the model when h is less than h bar. But again, of course, the whole discussion can be null and void unless you can prove that h bar is indeed strictly bigger than minus infinity, so that h bar is finite, right? And that is actually, of course, the more stronger you put here, the more difficult it becomes to prove the finiteness of those kind of estimates. But it was proven. But there is another problem we'll now face. So let's talk about that. So, okay, what would you like to prove? So remember, we'd like to prove that essentially the goal is, I think you have guessed it, that h bar, and it is clear that we know that this is less than a star, less than or equal to a star star. That we know. This information we have. So a star is strictly sandwiched between h bar and a star star. We would like to prove that h bar equals a star star. Okay. To do that, what do we have to do? We'll first assume that suppose it is not the case. Okay, suppose that this interval that you see there, that's h bar, the open interval between h bar and a star star, is, let's say, suppose. Suppose this is not an empty set. Starting from that, we would like to arrive at some kind of contradictory statements. Okay, that's the idea. But in order to run this argument, we'd like to have some information about this fictitious regime. Okay. Now, the advantage of the definition that you chose for A star star is paramount here, because it does tell you something very interesting, right? That when it, well, it tells you by some mysterious means that you have to believe now that when you're bigger than H bar A star star, you have this kind of sharp decay. But it immediately gives you something interesting when H is strictly less than A star star. It tells you that this infimum is positive, because that's the complement condition. So you get a uniformly positive lower bound on the analyte crossing probabilities. Okay, that's a very good thing to have. But you don't have something similar from this definition, because again, it's basically a consequence of the fact that this definition is very strong. So, well, it tells you very much when you are below H bar. So you have a big cluster, you connect them without going too far. But, well, what does it tell you when you are strictly bigger than H bar, when you don't have these properties, except that, well, you don't have that. So that's why we'd like to obtain a different characterization. So to this end, let me present this new threshold, kind of like pseudo version of the H bar, the mock version of H bar, which will of course later go on to show it's actually equal to H bar. That's this matter of the next lecture, hopefully. So what do I define here is H tilde D. So let me help you to parse this. What do I mean by that? So what is it saying is the following, that so UL is a subpolynomial number. Okay, forget about this particular choice of log L to the power 1/3 for now. Okay, it's just keep in mind it's a subpolynomial in L. It's very small, very tiny. So what it's basically telling you is that H tilde is something below which, when H tilde H is less than H tilde, what this thing is telling you is that the probability that this tiny thing, which you can almost think about, think like a point. So let's say this, something like that. Okay. So this connection probability, this is bigger than or equal to 1 minus epsilon to the over L to the over D. Okay. Let's say, right. So, right, yeah. So something like epsilon L, where you can choose epsilon L to go to 0, okay, along some subsequence. Okay. Now, what's the usefulness of that? What's the point of this? So look at this. Why actually 1 over L to this epsilon L over L to the power D? Well, L to the power D is exactly the volume of the box, right, of size L. So by a simple union bound, this would give you that you can say that you can place boxes everywhere, like here, 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 everywhere. By union bound, you can ask each one of them to be connected to the boundary. What this lands us in is the so-called called the everywhere percolating. So let me just say is it's not really everywhere, but sorry. Let me just do that. Is called almost everywhere percolating subgraph. So what this means is that, well, all these tiny boxes, which you can think of in our mind as points, almost point-like, they're all connected to the boundary. Okay, you have this picture, but they may not be in the, so you'll automatically have actually, okay, so this will give you with a very high probability, you'll have large clusters, okay, but not quite so as you require here, But there's another problem that is missing, which is the uniqueness. So, well, you are getting this existence with a high probability, but not quite this one. I'll talk about that later. But also you need this uniqueness, right? That any two big clusters are actually connected in a twice bigger box. To do that, so there's a paper, it's very good, is a paper by Benjamini and Vincent Tasio, Itai and Basu, in 2017 called the homogenization by spinking, But they do it, but they prove it for Bernoulli percolation. So if you start with them almost basically everywhere percolating subgraph like that, and you just increase your density parameter a little tiny. Okay, you just put a very slight percolation on top of that. So like epsilon, okay? And so this, you top something like that, some kind of epsilon is called epsilon splinking. So what does it mean is that you sprinkle some edges, okay, with a very small density or vertices. If you do that, what they proved is that with a very stretch exponentially high probability, all these clusters get connected, okay? It's just enough for arbitrary small splinting to connect them all. Okay, so that's the idea that we also use here. But remember, it's not Bernoulli. You don't have all the kind of nice properties that you would have here. You have to deal with dependence. There is a very strong dependence because it involves actually revealing some clusters. We'll have negative information and lots of problems. We'll touch upon that a bit in the next lecture. But you can adopt that idea to come up with a quantitative version of that to give you that with a very high probability, although not like stretch exponentially as small that you see here, you actually can achieve both of these properties is under the assumption h is less than h tilde with a very small splinking. Okay, so just decreasing the level by a little bit. Then what you do is start from there and you apply, do a renormalization to arrive at this probabilities that you see here. So this is not very clear, I know, but I'll touch upon very briefly in the next one. But believe that. So that proves it that h tilde is less than or equal to h bar, because you start from any h strictly less than h tilde, you have this condition, this almost every percolating picture, and you arrive at h bar at a strongly percolative picture that is that you should see below h bar. And but the other way, the other side is actually quite clear. Again, the argument that I presented to you last time, this one, if you remember, you can actually again try in your head that, well, this actually applies, and actually you can prove that you'll have very, very good probability of connecting, of having this picture under the assumption that h is less than h bar, thus giving you that h tilde is bigger than or equal to h bar. Okay. Anyways, so after this, what you know is that, let me just put it down here. So with this, that h tilde equals to h bar. Good. Any question? Okay. Now, but what is the good of that? Well, so let's recall both of these definitions here. This is h star star that we already saw, and then this is h tilde. Okay, and they are both phrased in terms of crossing probabilities. Now, this actually gives us quite a good information in this fictitious regime that we are talking about, right? Which you want to show that this one actually, this gap is really fictitious. This doesn't exist. And what are the informations that we have? So in view of this two definitions, well, one is that when you are below a star star d, as I told you, you have an uniformly, so you have the following probability that BL is connected to the boundary of a twice bigger box, infimum over L is bigger than or equal to some constant depending on H and D, that's strictly bigger than 0. Okay, that you have. Now, this is an argument, and actually if I get time at the end, I'll actually, because it's a very interesting thing to know, argument by Sarf, Raphael Sarf, in this paper in the Bound and Arm Exponent in 2015, where you can actually use this result for any, so suppose you have this property for any percolation model, okay? And you have some few more properties. So for example, you have, let me just write it down, FKG, which you do have, as I think mentioned it last time, for Gaussian fields, if you have a Gaussian process with non-negative covariance, you have FKG property. Okay, you have positive association property. Okay, and Gaussian free field, as you saw, its covariance is a green kernel, which is a positive function. Okay, so this property plus FKG plus lattice symmetry. So essentially the kind of rotation by pi by 2 and a reflection, essentially lattice symmetry. These are enough to give you this. These are enough to give you that point-to-point crossing probabilities if you allow a slightly bigger regime. So x and y are in a box of length BL, then you allow it allow the path to wiggle through a box of twice bigger size, but that's not a big deal, is bounded below by a polynomial linear. And this will be very useful, okay, as we'll see. Okay, and I'll try to talk about the proof if I get time at the end. Okay, so this is the consequence of h being less than h star star. What is the consequence of h being strictly bigger than h tilde? Well, now actually you have a good definition. So we know again that when h is strictly bigger than h tilde, this infimum, right, is positive. What does it mean? It means that this disconnection probability is also polynomially bounded below. Okay. Now, those of you who are aware of this kind of thing have seen this kind of before, and those who haven't seen, just don't bother. You'll know like this kind of properties are kind of characteristic of critical phase. Okay, on your critical phase, and so that will be the point. Okay, to show that you cannot have this kind of extended critical phase for a non-trivial interval. Okay, that will be the goal. Okay, so this is the question now: whether these two a priori different critical parameters actually do coincide. Any question? Okay. Now, how do you do that? So let's go back to some of history and in that regard. So what I call it here is taking one step at a time. Why do I call that? Is the following. The idea, the basic paradigm is something like the following. So you have a process that you somehow don't know what to do with, but that you cannot, that has a long range of dependence and potentially infinite range of dependence, but that you might be able to approximate, okay, locally on boxes of finite size with processes having a finite range of dependence, okay, and of course this range of dependence would increase, get worse and worse at the size of the box, okay. Now, if you can do that, probably you can think that, okay, for finite range guys, probably you can do something more because they're probably more, at least superficially, you can think that they're, more amenable to comparison with Bernoulli percolation. So you can do something like that. And then probably you can transfer those bounds somehow in some magical way to the original model, okay? So let's start from there, okay? So, but why you can think like that in this case, I mean, what are your analogs? What are your finite range versions or finite range approximations for your model? Well, in this case, actually turns out, in the last one, I mean, in the last talk, I talked about random methyl elements, and it's also true in that case also as well, but it's much more difficult to prove. Anyways, there is actually a very natural way to obtain finite range versions or approximations of Gaussian free field. Okay, so how to say that? So let's start from the covariance kernel, which is the green kernel for Gaussian free field, and what you can write it as. So what is Gaussian free field, right? So as we I think saw last time, it's essentially so let's see, yeah. So it's the expected number of visits starting from x to another vertex y, and you see, so it is easily seen to be written as a sum of probabilities like that. But what you can do is that you can write this transition probabilities as the transition probabilities at even step for a different random walk, okay, which is a random walk on the. So essentially, what you do is that the reason for this is, as I think probably presumably clear to you, is that I would like to obtain a square root. Okay, I would like to argue that each of these transition probabilities that we're seeing here is in itself a valid, it's in itself a non-negative kernel, so that you can define a Gaussian process with that covariance. So that's my goal. Okay, and for that, I just need to show that they are non-negative kernel, for which I just need to show that you can take a square root of that. And how do I see that? Well, what you do is that you can actually write. So you can write the L step transition kernels for the lazy random walk as the event step transition kernel of a non-lazy random walk on an extended lattice. So probably it's useful to know anyway. So let's see. So if you do your ZD, imagine what you can do here. You introduce this kind of middle points, the midpoints of the edges, and what you do is that you can think of the random walk doing the following. So your random walk on ZD, so it goes from one vertex to the adjacent one. Instead of doing that, you can decompose into two steps. So the first step, the random walk goes to a midpoint, okay, which is adjacent to it. And then the next step, he either chooses to come back, okay, that actually gives rise to the laziness of the random walk, right? So the random walk has a positive probability of being at the origin at one step, or it can choose to go to the next, the original lattice vertex, okay? In this way, representing the random walk, decomposing the random walk in this way would allow you to write every transition kernel as an event step transition kernel for a different random walk. And that's good for us. Now you will immediately know that you can take the square root of that, and you can define a Gaussian field, okay, with the central Gaussian field with mean 0, of course, and whose covariance kernel is same as Q12. Okay, good. So what does it mean? And remember, right? Okay, the covariance matrices for if you take the sum of independent Gaussian fields, the covariance matrix, the sum is the sum of the individual covariance kernels, right? So here you go. So in L2 sense, what you can obtain is the following. You can actually write in view of that phi, in distribution, the same as the sum of psi L, where psi L's are independent normal 0 Q2L. Okay, and this sum is defined in the L2 sense. Okay, now notice an important property of psi L. What is this covariance kernel? Its covariance kernel is Q2L. Okay, in particular, the covariance between X and Y, or for that matter, between any two sets. So it's an immediate consequence. We take any two sets S and sets T, such that the distance between them is strictly bigger than, let's say L. Okay. Then this definition is immediately telling you that for any X here and for any Y here, the covariance kernel is 0, right? Because that's, so recall, what is this covariance kernel here? Is basically the L step transition probability of the nearest neighbor random walk. Okay, so the random walk cannot travel a distance bigger than L in steps L, in L many steps. Okay, so what this means is that as long as two subsets, two sets, or two domains are L apart, they're independent. Okay, so you have a finite, so I have reduced, so the psi L's are essentially finite range. Okay, so what you do, the truncation now is obvious. You just take the partial sum of psi L all the way up to capital L, which is your preferred range of dependence. Okay, you thus obtain a capital L range analog or approximation of your original Gaussian field. Okay. Now, what can you say about this finite range fields? They are finite range, so you can, as I said, you can hope to be able to say that, okay, for this at least, all these kind of strongly non-parabolic regimes and parabolic regimes, they extend all the way up to the critical parameter, as you see, as you can find for, as you can prove for Bernoulli percolation. Now, the proof is not actually quite immediate, though it's, and let me emphasize on that, but it is indeed true. So you can similarly define these three critical parameters: H tilde, A star. Of course, A star is the usual critical parameter for the percolation, and A star, star, and H tilde are just defined as they are for Gaussian free field, except that you replace phi with a phi tilde L, phi L. Okay. Okay. So there are two parts to that. One which I call the supercritical part, because it's clear, because this demarcates a strongly supercritical regime, and this is actually proven in the classical way and adopting the classical argument by Gribent and Mastro that I talked about, that you use to prove the slap percolation. Okay, so for this finite range model, slap percolation again turns out to be the correct thing to do. Okay, this is not the infinite range model, so you can do that. You have to adopt their argument. For the other part, however, we don't know actually any way other than using this technology, OSS technology developed by Jumil Koparov and Tessio in their analysis math paper in 2019. So let me talk a bit about that. I think it's important in its own right. It's instructive, has an instructive value. So for Bernoulli percolation, as I told you, for Bernoulli, percolation, the sharpness, this exponential decay in the subcritical regime, were proved by Menshikov. I think in 86, where it proved that the percolation, if you define theta n to be the probability. So let me just say, so theta n as a function of the density parameter p as a probability that your origin is let's say connected to a box of radius n. Okay, then this theta n satisfies certain kind of differential inequality. So let me write that down. It's bigger than or equal to n over sigma n theta n times 1 minus theta n. And where sigma n is basically the sum of theta k equals to 0 to n minus 1. Okay, now there is nothing. Okay, now it's an exercise, and it's actually quite a hard exercise probably, and you can actually try that in your home if you want some fun. You don't need to assume that these are population probabilities or anything, as long as this theta n's, you have this, you have some converging sequence of increasing differentiable functions that satisfies this differential inequality, the systems of differential inequalities. Then you can actually prove that there exists some kind of parameter value below which theta n's will decay exponentially, and not only that, above which, so there exists PC. Okay, so not to confuse it, so I am calling it PC star because this has nothing to do with original PC. It's some kind of like some number. So you see, says that theta n p would be less than or equal to exponential of minus cp times n for all p less than pc, and for all p bigger than pc, you'll be able to prove that theta and p is bigger than or equal to, so let's say limit n tends to infinity, theta and p, this is a converging sequence, remember. So this will be the percolation probability, okay? For our case, it would be bigger than or equal to, I think p minus pc. So this immediately gives you that this pc star that you are talking about for your particular context is the critical parameter, right? This is a different characterization. Now, what Menchikov did to prove it is that he used a very geometrical way to derive this argument, this differential inequality for Bernoulli percolation. And the thing is that that really involved in a good way the independence of the underlying model, and that was not robust enough to, for example, to extend to other related models like, but nevertheless dependent models like random cluster models. So what Ugo, Ralphie, and Tasio did in this analysis math paper, but they used this Oasis thing, which actually appeared in an earlier paper, and one of the S is Schramm, as you probably might guess. They provided a way to use that inequality to derive Menchikov's inequality. And as a consequence of that, they proved it for the random cluster models on all dimensions. And as you can see, their techniques have been used for many, have found application in many other models. For our models, however, it turns out that this inequality is not the correct inequality, differential inequality. Okay, so you cannot use OSS to obtain that. But for these finite range models, actually, you can adopt their technique, this technology, to come at some form of inequality like this. Okay, using which you can similarly obtain exponential ticket, for example. Okay, of course, these prefactors will get worse and worse as L becomes larger and larger, because they have become more and more like the Gaussian field. Okay, so that's kind of aside. Fine. So for phi else, we know we have the nice properties. Now let's ask the naive question. Okay, let's take a leap of faith. Let's ask whether this phi bigger than or equal to h is a good proxy for phi bigger than or equal to h. So okay, so let me tell you another thing is that, and that actually can just be obtained by convergence by the the heat kernel estimate of random walks. You can actually show that phi is a very good approximator. So approximates phi very well, but on boxes of size length L, maybe a bit bigger than that, but around that on BL. Okay. So locally, so at the scale which is commensurate with the range of dependence, they can approximate the original field very well. But of course, all the events that we're interested in, they're involve the entire lattice. Okay, so this doesn't quite give you. Of course, you cannot do a union bound, let's say, or something like stupid union bound over all the boxes. That will give you infinity. Okay. Now let's ask a naive question, nevertheless, that is it true that this model is some kind of a good proxy of this original model? So we can probably transfer the results from one to the other. To this end, let me try to convince you that it is not. So one way, so what do we mean by a good proxy? Okay, so let me get back to this one. Okay, one way of good proxy would be is called something like you will be using the idea of stochastic domination. stochastic domination. I think many of you already know this thing, but let me spell it out again. So what does stochastic domination mean? This in this context, and you can actually extend it to any partially ordered sets, is the following: that let's say you have two percolation measures, it's a P and Q, and you say that P is stochastically dominating Q if probability of all increasing events, so epsilon is increasing, okay, is bigger than or equal to that would be Q, of course, Q of E, okay. Another way to see that is that, which is an equivalent characterization, is that there will be a coupling. So this is an alternative. Alternative description. There exists a coupling lambda of P and Q such that under lambda, so what does coupling mean? As you know, is that under lambda, the marginal of omega would be P and the marginal of omega prime would be Q. This is this is one, okay. So you can couple it away so that omega prime is always smaller in this partial order with respect to omega. Okay. Now you can hope that one way these two models would be comparable. Okay. So for example, let's say the following. So let's say let us denote the model. Okay, so use this one. It's quite possible you can ask that whether or not this phi bigger than or equal to h, let's say it stochastically dominates some kind of Bernoulli percolation with some parameter p of h. So I think let me use it Bernoulli. Some Bernoulli pH, and also it dominates because we really would like to sandwich it, right? We really would like to say that this is not just one direction, but this can be compared in both directions. It also, the following is true. Plus epsilon, because the direction is opposite. Okay? Where epsilon you can make arbitrarily small. So this is a question that we can ask. That would be a first way to do direct comparison between the two models. Now, unfortunately, this doesn't hold. And let me immediately try to prove to you why so. So let's look at this event. So under any Bernoulli percolation, probability that a ball, let's say of radius n, is open, means all the vertices are open. So it's like p to the power volume of Pn, right? Because you just require everything to be open, which costs probability p and you multiply. Whereas, let's look at what is the same probability for this Gaussian free field. Open in phi bigger than or equal to h. Okay. Now, so essentially this means that phi x is bigger than or equal to h for all x belonging to Bn. In particular, this implies that if you take the average of this in Bn, this is also bigger than or equal to h. Now this one is actually very easy to evaluate. Why? Because it's the sum of Gaussians, right? So you have very precise estimate about the covariance kernel, so you can actually obtain what is the precise distribution of that. And let me just tell you, you can just do the computation at home. So this is something like n of 0 times the capacity, and I'll come to that what capacity is. It's a kind of content measure. The last of my lecture of Pn. But what is important for us to see that they don't really compare is to see that the capacity of Pn is actually of the order of n to the power b minus 2. Sorry, it would be 1 over that, okay, of course. Okay, what does it mean? So essentially what you are asking is that probability that normal random variable x, which is 0 and which variance is something like c over n to the power d minus 2, that is bigger than h, and here let's assume h is bigger than 0. Okay, so by standard Gaussian tail bound, this will immediately tell you this is of the order of exponential of minus c h squared into the power d minus 2. Okay, so you see this order is markedly different, okay, from the volume order exponent that we saw for the Bernoulli population. And you can actually obtain the similar matching lower bound, okay, with a log factor possibly. What does this tell you is that you cannot compare those two models in this way. Okay, right. So that goes out of the way. Then you can ask me, well, we don't need probably that strong notion of comparison. I mean, we just care about connected probability, connection probabilities, right? And maybe, even though what you are showing me is basically, like this kind of bulk events, but we don't need that at all. So maybe in the weaker sense, they are good proxies of each other. There are such inequalities. So let me tell you the answer first, as spoiler, that even after this lecture, and even after this work that we did, we really do not know anything like that. Okay. But to give a tribute to the historical succession of ideas, let us assume that, take a step towards that. Let's try to assume that something like that can be done. So let me try to present you this result, right? Which is the main core proposition for this part. Okay, so again, let me try to help you to parse it. So what it does is that it says that, yeah, it indeed appears that you can actually compare connection probabilities with the same for this truncated model, introducing a little bit of splinking, a little bit of this kind of wiggle room of epsilon, which you can make arbitrarily small, and introducing some kind of additive error, which is very small anyways. Okay, it's very small. It's exponential in log to the 1 over 3. It's as small as you can. Yeah, it's quite small, not exponential though. Okay, so then why did I say that we will not know? And the reason lies in this particular caveat. This only holds this kind of comparison, assuming that you are situated well within this fictitious regime, okay, that we talked about, H tilde and H star star. And as I'll try to now convince you that this result itself, and in conjunction with this this bounds that we just, in this proposition that we just saw, they imply that this interval is actually empty. So this statement is actually void at the end, which is ironic. Okay, so let me quickly try to convince you. So assume that H tilde and H star star are indeed different. Okay, so let's take the midpoint of this interval then, and let's take a very small width, okay, which is the width divided by 10. Okay, now here substitute for H the value H0 plus 2 epsilon. Notice that this definitely lies strictly less than H star star minus 2 epsilon because of this chart. Well, but then I can apply, because then I'm within my wiggle room within this fictitious regime, so I can, this is valid. Well, what do I get then? I get a lower bound on this probability. In terms of what? In terms of the same lower bound, H0 plus 2 epsilon, for the Gaussian field. Well, but what do I know about this H? This particular H here. H is H0 plus 2 epsilon. Well, I know that this is strictly less than H star star. Okay, and that means I have a strictly positive lower bound on that. In particular, now this is very small, right? This actually, so here R, remember what we're doing here, you can imagine capital R to be twice R, right? That's the definition, if you remember. From this one. Okay, very nice. So you put that, and so this is really, really small. Of course, no way you can beat the constant. So you immediately get a uniformly positive lower bound on this probability. What does that mean? That means that your H star H0 plus epsilon by definition is below the H star star analog for L. Okay, that's there. Now do the same thing here in this bound again with H instead equals to, I think, H0 minus 2 epsilon. Okay, do the same thing. Again, you can just verify similarly because epsilon is small that you have all the required condition, and this immediately gives you again a lower bound on this in terms of that. The same for in terms of the same for the Gaussian field, but again you are above H tilde. So that means this is bigger than or equal to some constant. Remember the definition, some constant times r to the power t. So you get the same bound for this one as well. But that immediately tells you, well, H0 minus epsilon then has to be bigger than H tilde value of L, phi L, because that was the definition. And you immediately reach a contradiction, okay? Because you know that H star star L is actually equal to H tilde of L. Okay. I don't know if that was too quick. I can repeat it if you want, but that is sort of, you do the standard things and you get it from there. So okay. So that is the funny part of this result. You see, you start from a regime which doesn't actually, you ultimately end up proving that it doesn't exist. Okay. So now I'll come to the proof in the remaining time period that is left to me. So let's see, how do I prove it? Okay, so what is the idea? How do you do this? So this is the goal. We'd like to compare this connection probabilities as it's clear, okay? Introducing probably a bit of wiggle in this parameter value. To do that, the idea would be, well, not immediately jump, from phi to phi L, but do it in step-by-step manner. So what do we mean by that? Okay. So remember, again, this kind of truncation. So introduce a scale of scales, Ln, which goes geometrically. And write phi L, okay, this as a sum of the differences. Okay, so the main idea is that, okay, as you see here, you can write phi L as a sum of the telescoping sum of the differences of the field in successive layers. Now, what's the point of that? What does this phi L minus 1 consist of? They actually consist of this, independent field psi L's, that we saw earlier, okay, which are independent. So all the fields that are, all the psi L's that are, being clubbed under these sums are actually independent, okay. So what we get here is something like this. So we have independent Gaussian fields, and what is the nature of covariance between these fields? Well, the covariance between Zxn and Zyn, they're basically, the sum of the transition probabilities between scales Ln minus 1 and Ln. In particular, they vanish as soon as the 2 points are further than Ln apart, right? Because all the transition probabilities are 0 there. Okay, so in particular, the range is Ln. They satisfy FKG, well, obviously, because as I told you, the rule is that for Gaussian fields, if you have a non-negative correlations, you have FKG, and of course, these are non-negative, and there are some more properties, but we'll come to that later. One important thing is that, and which I didn't specify quantitatively last time is that the variance of xi xn is decays polynomially in Ln. Okay, so it actually converges quite fast, if you see. But although, in domains, you can, with a size which is commensurate with Ln. Okay. So what is the idea? The idea is that let us look at this connection probabilities and slowly scale up the range of dependence. Okay, so that's the idea, and somehow transfer this kind of comparison along the way. So this is encapsulated in this statement. So we'd like to do some kind of interpolation. Okay, so let's set to two successive scales, Ln minus and Ln, and take their linear interpolation. Okay, and notice what we really need to do is that, well, if you consider this, if you go up t, and we actually change the threshold value accordingly, with a bit of small prefactor, and prove, and we are able to prove that as we change t, so in a sense you can say that t is kind of like the degree of dependence, range of dependence. Okay, so by increasing t, we are increasing the range of dependence, and at the same time, of course, to compensate for that, we would like to change the threshold. So let's say if you want to obtain an upper bound, let's say you want to prove that the connection bound increases, you would like to decrease, you would like to decrease the threshold so that you can get a bit more freedom there to be able to compensate that value. But we would like to say that as you go up and up, as the scales become higher and higher, but because of course, you will have to be able to compare them with arbitrarily small epsilon, okay, depending on L, okay? So the idea is that this epsilon, and we should be able to make them smaller and smaller as n becomes larger and larger. That's the idea, okay? So in particular, you can take any summable sequence, which I take at 1 over n squared, okay? So that's pretty natural thing here, but how do you do that? Well, one way, and you have already seen from Tom's talk, to do these things in percolation theory is to go via differential inequalities. Okay, so let's look at this 2-point function th, where t is this kind of range of the proxy for the range of dependence, and h is the threshold. And you'd like to say that q and t, and appropriately adjusted h, they increase or decrease depending on the sign. If you okay, and you can actually probably try to quickly convince yourself something like this would be ideal. Okay, what we really want to say here is that the change in this probabilities with respect to this t is very well compensated by changing the threshold value h ever so slightly. Okay, that's the point. In other words, the gradient with respect to t is very small with respect to the relative to the gradient with respect to the threshold. Okay, I put a negative sign here because remember there's a decreasing functions of h, right? Because as h increases, the model becomes thinner. So that actually reacts. Okay, very good. If you have that, then life is very nice. So what are these things? What are the probabilistic interpretations of these gradients? And here again, Tom's lectures would be useful for you. He already talked to you about the pivotality, the pivotal events. But let me just state it here a bit more general context, since there's because it's not really Bernoulli percolation. Okay, so remember that Bernoulli percolation, you can obtain also as level sets, right? You can obtain them as level sets of, let's say, uniform random variable, which defines the grand coupling, right? The coupling of all the percolation model. So, for example, to design Bernoulli P, you'll just look at ux, let's say, bigger than or equal to 1 minus p. So that's another way of sampling them. Actually, you can also could have chosen independent Gaussian variables, But here, of course, we would then actually the parameter range would be not P, but it would be a reparameterization of R minus P. But the point is that you can sample a wide variety of population models using level sets. Anyways, okay, so let's say H of P. Okay, so let's so instead, suppose we have level sets of some fields. Okay, so like here we have phi bigger than or equal to H. Okay, now in order to do so, let's try to obtain the Russo's formula very quickly just to see how does it work. So you have, let's say, an epsilon, a monotonic event. Okay, and the way you would differentiate it is just by using linearity of derivatives. So you just differentiate with at a particular point with respect to the threshold parameter. So our event can be described like this, right? Sorry. Belongs to epsilon. So if epsilon, this is the event that let's say 0 is connected to the boundary. This is that. Then it just says in the level set bigger than or equal to 0. This basically says that phi minus, so it's in bigger than phi minus H bigger than or equal to 0 in particular phi is bigger than or equal to H. Okay, and there actually what you do the regular thing. So you'll get by monotonicity the limit of epsilon goes to 0. Probability that phi minus H minus epsilon 1x, you just change it at one point belonging, sorry, I was mistaking this, belonging to epsilon, this event, minus the probability that phi minus H belong to H divided by epsilon. And now using monotonicity, monotonicity, this is exactly equal to epsilon, the probability. So what is happening here? This is a monotonic event, so you can take the difference of these two sets. One thing is, of course, that H plus epsilon is strictly bigger than phi x, because that's only when you will see a difference between these two events, right? Because we are only changing the threshold at a particular point x. And PV. Why so? Why PVX? So what is PVX? Let's go get back here. PVX is the same thing that we saw in terms course, that which essentially says that the point x is pivotal for this connection event. So more geometrically, you have two open paths, right? Connecting x to the two sets that you want to connect, like the boundary of B capital R and the B little r. Okay, and the path passes to x. But on top of that, you also have the dual surface, right? Kind of a closed guard set that passes to x, so that if you close the vertex at x, you no longer have any connection. So x is the only way to travel between the two sets. Okay, so this is the event, and for these two events to be different, x has to be the pivotal point, right? Because you're only changing the threshold value at x. You're not changing anything elsewhere. So that's the pivotal point. And then, so what you get from here, sorry, let me just check it. So what you do here, you just take the conditioning. So this, when you take the ratio with respect to epsilon goes to 0, what you'll have if you take the conditioning out, so let's say, let me put it there, what you'll have here, you'll have a probability of PVX, okay, and you pull out this event as a conditioning. So you assume that there is some continuity, non-degeneracy in the underlying field. So conditioning on this under this is same as conditioning under that, times limit of epsilon goes to 0. You'll have this probability that the field lies between H plus epsilon and H. Which goes to, of course, the density, right? So which of course by definition, the density, the underlying probability density of the. So let's say P of, let's see what I used here. So F of phi th, okay? So that that's close to the F, the density of phi at H. Okay, density of the probability distribution. Okay, and you see the Russo's formula for Bernoulli actually follows very easily from this. From that case, the phi is uniform. Recall that. Remember, just notice that we don't need anything about Gaussianness in this thing. We just need a non-degenerate, like, continuous distribution having a density. The density of uniform is 1, and this conditioning doesn't bother to you there, but it will bother you here. We'll come to that short. Okay, so here you have this kind of expression. That's why you get this. And by chain rule, okay, notice the similarity between H and T. By chain rule, you can apply the same procedure, and what you will get, a very interesting thing, is the covariance term between the field value, okay, and this the difference between the two successive layers, okay, which is this one, with the fidelity. Okay. Now, okay. Now suppose we are in Bernoulli percolation. Okay. In Bernoulli percolation, you will already know from Tom Stock, this event pivotality is actually completely independent of the state of the vertex at X itself, right? Well, because this is a completely geometric picture. This is nothing to do with whatever happens at X. So if you are in a Bernoulli, where phi tx would be your uniform or something like that, well, this unconditional probability, this conditional probability will just be unconditional probability, because this condition doesn't matter. And here also, pivotality would be completely independent with the uniform, the field value. So they will be just totally decoupled. Okay, so and hopefully this expectation, at least for our case, is very small. This will be small because of this reason. Let me just tell you why this expectation. Forget about that. If you didn't have this, why this expectation is small is because of this. Okay, okay. Then actually we'll be all merry, and this will be a drag problem, not worthwhile, and you will immediately get this. But of course, that's not true. Right? And why that is not true is, of course, that the fields are heavily dependent, and the range of dependence is as large as Ln. I mean, that actually goes to infinity, because that's the point, right? We never go far from actually getting anything close to this. So we have to do something different. We have to take care of the dependence between these two to be able to compare to that. Okay. So then comes the idea. Okay. So, well, first of all, let's do something. Again, so just recall that, that we'd like to compare these two. Okay. And we'll have to, the way we'll see, we have to compromise. We cannot really get this one, and as you can see, because if we got that, we will have this kind of error term. But do. Okay. So let's get back there. I think in the remaining few minutes, I'll be able to convey the main idea. Yes. Okay. So there are two. Let's split into two parts. The first part is, okay, so this is what I told you just like that. Now let's look at this one. The first part is that if psi xn was always very small deterministically, then of course we will have no problem. Okay, so for example, in particular, if it was less than 1 over n squared, or some other sequence for that matter, which was so that the tail sums can be made arbitrarily smaller to accommodate smaller and smaller epsilon in the difference in h. Well, then I could just do this step and stop. But that's not the case. So this is the convenient part. And there is another part, which is that, well, where actually really the troubling part, which is basically the tail of psi xn, where it is actually can be bigger than, it can actually can be bigger than into the minus 2. And we have to look at the covariance between these two. So how do you do that? Okay, so this is actually what we want to prove, as I told you. The idea is, okay, we cannot decouple, of course. We cannot factorize this into the the productive probabilities, as I told you, because pivotalities do actually depend. They actually are correlated to this event. But can we do something so that maybe we can replace this pvex event by something weaker, so that we can push the support of the event far away? Because remember, although xi xn has a range, I mean xi xn is a big range, but it has a finite range. But that range indeed can be as big as possible. That's true. So of course we have to do what? But the first step might be push the support of this even p of x too far away. So what do I mean by that? So let me quickly come to picture, I think, because otherwise it will be one. Okay, here it goes. So what do I do here? So this is a different even than pivotality. This is what I'm calling quotes pivotality. So what I'm doing here, so remember in pivotality, what you have is that you have this path coming all the way to x, and also this this dual surface extending all the way to x. Okay, but that we cannot do because, well, that's dependent on the field xi. But we know that the range of dependence of xi xn from our condition is a ball. You know, it's a ball of radius L. Okay. So what about we forget, we push the support of p of x outside this ball. So what do I mean by that? So what do we do in this geometric picture? I forget the portion of the path in this ball. Okay, that gives me one one removal, and also forget this dual surface inside the ball. In this way, we arrive at an even which does not depend on the state of this ball. So it's a coarse version of a pivotal event. Instead of a point being pivotal, your ball is pivotal. What it means, you just apply the same thing. You just substitute a point for a ball. So if you close this ball, if you declare all the vertices in this ball to be closed, you don't connect, right? Because you have the dual surface. Or alternatively, if you open all the vertices in this ball to be open, declare all of them to be open, you connect. So that's a coarse pivotal. Okay. What is the advantage of doing that? Well, we achieve the decorrelation. We could factorize now. We just, first actually there is just monotonicity, right? So this is less than or equal to 1 coarse PIV, because that's just inclusion. Then, well, when we arrive at that event, then I can go there. So I just decorrelate. I can just now factorize this to even, and this is unconditional because, well, again, as I told you, the coarse probability doesn't depend on phi tx, and you end up with this expectation, which is very small, which is written here. Okay, that's just Gaussian tail bomb, nothing else. Good. Well, but we cannot, of course, declare, far from declaring anything resembling victory. Of course, we have to come back to this pivotal event because that's actually what we want to do. We want to often come back at the pivotal event, like point pivotality. So how do you do that? So what do you have to do? We have to reconstruct pivotality. And how do we do that? There are two parts in reconstructing pivotality. First, as you can see, there's an increasing part, which is that connecting the path. And the second part is that connecting with the dual surface. Okay, this part is actually quite hard in regular thing. This part also not easy, but well, you can see connecting paths may be more easier in general than constructing surfaces. But so these are the two steps that are drawn here. Okay, so you first would like to draw a dual surface, and then we would like to connect them using a path. Okay, of course we cannot just do that. So let's see why this is reasonable. At least why they are reasonable, and then there are other things. So here, this assumption comes to the fore. We are in this regime H tilde and H star star. Since we are bigger than H tilde, remember we have a deconnection probability. So let's just recall. I think here I wrote that. So I think it's sorry. Yeah. Recall so that this thing that you have a polynomial lower bound in disconnecting two regions. So that can come handy in constructing this one, hopefully. And for the next step is that creating these connections. For that, we'll use H less than H star star, for which this one can come handy. This a priori estimate, which is actually enabled by assumption, being in this particular region. Okay, but you cannot quite do that. You see, you not just connect two things, right? while you do connect, this is not really an unconditional thing that you just take 2 points and connect it. You have to reveal some amounts of the cluster. And they are extremely, so they give you a huge negative information. So when you reveal a cluster, at least this part, or let's say you reveal this dual surface, a bit of that gives you a huge amount of negative information. And remember, the field is heavily dependent. Okay, so you cannot just just blindly apply that. For that, you need new gadgets. And to this end, let me present. Okay, I'll present to you, which is called the bridge, multi-scale bridge. Hopefully, I'll have time today. But if not, let me just present. Okay, let me just tell you anyways what I'm going to do here. Okay, so the first step, the constructing the dual surface is easy. So let me tell you what. So here, look at this picture. So we're in this. We're in this picture where the coarse pivotality is contained in this event. So let me describe this event. So we have forgotten the path outside a certain ball. So these two paths come all the way down to this ball. And we have forgotten the dual surface inside the small L ball. Okay, that's what we have done. Now we have to close this surface. How do I do that? That I can do in the following manner. I have a very good bound, polynomial lower bound for this event. Okay, so this capital M is basically, I think I told you, it's kind of the inverse function of U. Okay, remember that I defined U of L to be e to the power log L to the 1 over 3. So it's just basically the U inverse. So your L is U of N. So that's the idea. Okay, so let me just write it. So L is, M of U of M equals, so that's it, because that's your smaller ball here. Okay, so what do? You can actually use this bound to create a surface like that. Now, why you can do that? And paying a past, why can do that? The reason is FKG. And again, the question is, of course, here, if you're careful and if you're aware of these things, well, you are doing a conditional FKG, right? Because potentially we're conditioning on several informations because there are informations about the blue clusters, there are informations about these red clusters. But the thing is that as long as you push this increasing information away, all the information that you're left with inside are basically negative information, that you have a dual cluster, a dual surface extending all the way up to this ball, and on top of that, you're requiring another negative information. That is, you want to draw a closed guard set. Okay, so that's why you're able to do that, bring polynomial cost in it. Okay, so that closes the dual surface. So you are in this picture. Now, what you have to do, you have to create, you have to actually be able to close this gap. You have to actually pull these paths inside. Okay, now actually I'm finishing my time. Probably I'll end up the last next time. So here, what happens, there are two stages, okay? The first stage is that, remember, well, you can say, okay, why dependence is, okay, I can just start from here, and this distance, how much distance is that? Well, distance is like mn, but that's okay. Distance is like mn, which is like e to the power log ln cube. You say, okay, that's very nice, because that's not too big, right? Because I have already a prefactor. So remember, what do we have there? So if you remember, what we got here is that when you decoupled, we have a very good state exponential prefactor. Okay, so whatever the extra cost that comes in its way to be converted to a pivotality event, as long as that is that can be killed by this state exponential factor, we're good. So in particular, we can pay all the way up to state exponential. Here you can say, okay, that's nice. So this is very small. This is anything but state exponential. So I can just start from there, and I'll just just open them one by one to come all the way up to this kind of dual surface. Okay, and then I construct it, just paying this cost, just like we do in Bernoulli percolation. Unfortunately, there are two problems with that. One is that the field file, okay, so, well, of course, the thing is that the problem is you have a dual surface, a potentially negative information, right? And as I told you, you don't have really this kind of like finite energy properties for this kind of processes. How do you do that? Then you can come back to me and say, well, I'll not do one by one, but I'll of course be smart. We have to use this fact that H is less than H star star. Actually, I can connect faraway points that I already know. So why should I bother? I just connect this one to this one by a path. Well, that's right. But again, that was true unconditionally. Again, here you have conditioned, you have already revealed the surface, which gives you a hell lot of negative information. How do you get rid of that? Well, you can again come back to me and say, okay, the field is not actually infinitely independent. Infinitely dependent. We are working with a finite independent thing. So maybe I can take a neighborhood of that. So I can stay away from this by a distance L and perform my computation. I can go all the way up to here very easily. Probably my dependence doesn't bother me. There is a problem with that, of course, because this region itself is random. But let's assume you can do that. I give it to you. But what about the rest? How do you penetrate this remaining distance? Then you cannot play your trick. Then you really have to deal head on with this strong barrier of negative information. The remedy for this lies in the fact that this surface is very long. You have a long exposed surface. And hence, you can actually find some tunnels. And let me just say that. I'll expand on that next time. Some tunnels where the effect of negative information is not that bad. Okay, this is a completely deterministic statement, a kind of geometric statement that you can prove. And there is a probabilistic part of that, but the idea is that you can find this kind of quasar, which you call quasar, and once because it was done in Paris, and secondly is because the structure that you have a fat things in between and tapering off towards the end, where actually the effect of the negative information would not be too forbidding for you to not allow drawing paths to them, and I'll explain to them later on, so that you'll be able to find this kind of things with a very high probability, and then through them you'll be able to pretend as if you don't have any negative information, as if you're unconditional, and you will be able to draw this kind of paths to come all the way up to this dual surface so as to create a pivotal point somewhere here. And so that actually will give rise to an equation like that, which should ultimately would lead to a differential inequality of the form this with a bit of additive terms, a lot of other additive terms. Okay, so that was a bit quick. Next time I'll start a bit more on that and then actually go to the renormalization part. But I think I'll stop here. Thanks.
Okay, all right. Thanks. So let's thank the speaker, Subhajit Goswami.